So we came up with this separation of variables, and we had the formula f prime prime psi divided by f psi is equal to g prime t tilde divided by g tilde t tilde is equal to negative lambda squared. And let's do it for the g first. G prime t tilde is equal to minus lambda square g t tilde, right? And what is the solution to this? G t tilde must be an exponential function, C1 exponential, minus lambda squared t tilde. That's it, right? Yeah, let's call it C, because I'm going to call the C1, C2 for the constants of the f. And from this one, f prime prime psi is equal to minus lambda square f psi, and you know that it must be a sinusoidal function. So f psi must be a linear combination of sine and cosine. Which is lambda psi, right? Now we're going to write down the boundary conditions, right? And one of the boundary conditions is boundary condition 1, psi is equal to 0, theta is equal to 0, right? And if you plug in the psi is equal to 0 in theta is equal to 0, you find that the f of 0 times g of t tilde for any t tilde must be 0. From here, f0 must be 0, right? From here, we find that c1 sine 0 plus c2 cosine 0. This is 1. This is 0. So we get c2 is equal to 0. c2 is equal to 0. Right? And at psi is equal to 1, theta is equal to 0 again, f1 g t tilde for any t tilde. Thus, f1 must be 0, because if g tilde t tilde were 0, it would be a trivial solution. C1 sine lambda times 1 plus C2. I don't have the C2, so I don't need to write it down. We found that the C2 is 0 already. So from here, what do we find? Any idea? Is it the C1 which is 0 or sine lambda which is 0? Any guess?
So sine lambda.
Sine lambda. Why is that so?
Because C1 makes it trivial.
Exactly. If C1 were 0, being C2 being also 0, that would mean f psi would be 0 no matter what, and that doesn't make sense. I want the f to change with the psi. I don't want it to vanish. And if it vanishes, the entire thing vanishes. Theta would be 0 for all the values, and that doesn't make sense. So 0 is equal to sine lambda. Okay. Since C1 cannot be 0, to avoid trivial solution. Okay, good. So how can I make the sine lambda 0? Lambda can be any multiple of the pi, right? N times pi. This means that lambda can take infinitely many values, and I can label those values by n. So I can call the first lambda as, for example, pi, the second lambda as 2 pi, and so on. You should also include the negative numbers as well. So n can be 0. It also gives you 0. N can be negative, so that, for example, the sign of negative pi is also 0. So let's say n is an element of the integer numbers. I don't have one particular solution. I can have infinitely many solutions, but I can label them simply with n. So my solution, theta, is going to be not only f psi g t tilde, but I'm going to have different values of fn. So I can have f1, f2, f3, f4, blah, blah. Since for different lambdas I get different g values, I can also index the g values, but it's going to be just a superposition of those, and I need to basically use some constant bn. Okay. So my solution should look like this. So basically, in the previous attempts, let's label these lambdas by lambda n. Let's label this corresponding f as fn. Okay. Okay, good. If I write down the solution for fn and gn that we found earlier, I find the following. Fn is nothing but c1 times sine lambda n psi, and lambda n is n pi psi, right? Times the gt is just some constant c times exponential. It's minus lambda squared minus n pi squared t tilde. There you go. And one more thing. This is all constant, right? So why don't I just absorb it in one single constant? So I can just absorb all constants within Bn. My solution should look like n Bn sine n pi psi exponential minus n squared pi squared t tilde. Okay. One more thing. Now I should decide whether n can take negative and positive values. Now have a look at this. If n takes negative values, okay, like for example, instead of +2, if it takes -2, okay, so this thing becomes, for minus n, it's equal to, or n replaced by minus n, you get this one minus sine n pi psi. And this would be again the same. This would be again the same, but you would have a minus term. So you would get something like bn minus b minus n. So you can only take into account the non-negative values, but your constant would be different. But you can still make the similar summation. That's what I would like to convince you about. So I can say that, and for n is equal to 0, it's going to be just trivial. It's going to be 0, right? So n can start at 1 and can go up to infinity if I like. Okay, I can write it in this form. Now the task is to find the values of Bn. Okay,
Excuse
And
me,
now,
Professor.
yeah,
I have a question. So, since
sure.
the BN that is below is different than the one on top, can we use a different notation or something
Yeah, you can, but I thought it. I mean,
like CN because we are adding
exactly,
apple cost constant?
exactly. So here's the thing. Since Bn is just a constant in an innocent constant, I mean, there is no harm to. And also, I'm gonna forget about the previous Bn. It should not be a problem. I just thought about it. But yeah, let's make it. It doesn't matter for the sake of simplicity. Let's say Dn. Okay. Okay, yeah, you can do it. But as I said, since we are already going to forget about the previous Bn, we are going to forget about it. That should not be a problem, okay? If I had used the same Bn and the new Bn under the same setting, that would be a problem, okay? Okay, is that clear, Domingos?
Yes, it's clear. But I was
Okay.
thinking it will be like always the same.
Okay, good. Okay, now I need to use one more condition that I have not used before, right? To be able to solve for Bn. There is one condition that I did not use. I used the boundary condition 1 and 2, but I didn't use the initial condition. So let's use the initial condition to solve for the Bn's. At t tilde is equal to 0, theta is equal to 1. And that's equal to, for theta 1, what does this become? I'm sorry. What does this thing become for theta is equal to 1? It becomes the sum over n, starting from 1 to infinity. Bn sine of n pi xi exponential minus 0, which is 1, right? So we find that Bn's are such that it satisfies the equation 1 is equal to sum from 1 to infinity Bn sine n pi xi. Now, how am I going to be able to find Bn? How can we find Bn's? Any suggestion? Now remember that we solved a similar problem and we were able to decouple each and every Bn's in that problem. We had a like series sum of Bn's or An's, whatever, and we were able to decouple and find out each and every Bn by using orthogonality, right? We knew, so we know or we learned that sine n pi xi are orthogonal functions, right? We have actually, I have shown you a way to like demonstrate it. I'm not going to do it again because it's the same function. I don't need to redo this. So I can use the orthogonality relations, which is summarized as sine n pi xi sine m pi xi d psi from 0 to 1 is equal to 1/2 if m is equal to n. You can do this actually integral and see by yourself that when m is equal to n, you get 1/2, and you get 0 if m is not equal to n. This is for m and n are positive integers. Okay. When you include the negative ones as well, then if m is equal to negative n, you can still have the 1/2. You can still have the non-zero term, but that's the reason why we want to exclude the negative values. So since I'm excluding the negative values, I should be fine. Okay, I'm only comparing the absolute values of m and n, and in that case, you're going to see that this integral gives you 1/2 if m is equal to n, and gives you 0 when they're not equal to each other. Okay, so this is the orthogonality relation. Okay, and there is a name for this thing, this function. When two things when two things are equal, you get a non-zero value. When two things are not equal, you get a 0 value. This is called the Kronecker delta. It's 1/2 times the Kronecker delta mn. Okay. It's similar to Dirac delta function, but the Dirac delta function is for continuous sums like continuous variables like x and y. But the Kronecker delta is for discrete values like integers m and n. Okay. So how are we going to make use of this? We are going to basically take the integral of this equation on both sides with respect to sine m pi psi, so that I'm going to get rid of all the terms which are not equal to m, but only the term which is equal to m is going to survive. So let's write it down here. We're gonna make use of this. So let's do this one, the one that we actually inputted our initial condition, and take integral of both sides using integral d psi sine m pi psi. Okay, and we get on the left hand side, we get integral d psi sine m pi psi is equal to sum from n is equal to 1 to infinity bn integral d psi sine m pi psi sine n pi psi. Okay, and we know that this thing from the orthogonality relation is equal to 1/2 the Kronecker delta mn, meaning that 1/2 if m and n are equal to each other, and 0 if m and n are different. So we get we should do this integral as well, and that gives us minus cosine m pi psi divided by m pi from 0 to 1 is equal to sum over En 1/2 delta mn, n is equal to 1 to infinity. On the left hand side you get 1 over m pi minus 1 to m divided by m pi is equal to, now this one, this entire thing. So we're basically summing over all the n's, right? So you're going to have something like b1 1/2 delta m1 plus b2 1/2 delta m2 and so on. But we know that it's gonna vanish unless the term becomes equal to m itself. When you get the delta mm, that doesn't vanish, but all the rest of the terms actually vanish. What does it mean? It means you get here the bm m term 1/2. That's it. That's what you get. And the rest of the term actually is 0. So you have bm 1/2. So from here, if you solve for bm, you get bm is equal to 2 over m pi times 1 minus 1 to m, right? If you replace this in the original equation, so we found the bm, now we can actually place it here, right? And we get theta is equal to sum over from n is equal to 1 to infinity 2 over m pi. But by the way, since bm is this, you can actually, the m is a dummy variable, so for any m index, so you can replace it by n. It doesn't matter. You can make all the m's n. That's just the recipe, right? Okay, so you get mn, because my dummy variable is n for this case. I'm using the, n pi. Okay, there you go. N pi, parenthesis 1 minus 1 to n, sine n pi xi exponential minus n squared pi squared t tilde. And you can actually see that the even values of n vanish. The terms with even values of n vanish, since 1 minus 1 to 2k is equal to 1 minus positive 1, which is 0. So it's only the odd numbers, odd values of n which survive. So you get theta is equal to sum from k is equal to 1, 2 divided by pi times 2k minus 1. For k is equal to 1, you get the first odd number. For k is equal to 2, you get the second odd number, and so on and so forth. Sine 2k minus 1 pi psi exponential minus 2k minus 1 squared pi squared t tilde. Okay. Okay, let's see. Yeah, so one more thing. I should include the 1 minus minus 1 to n, right? This gives you actually 2 for odd numbers, okay? For odd n, what happens is basically 1 minus minus 1 to 2k minus 1 gives you 1 minus minus 1. It gives you 2. So you basically have 4 here instead of 2. Okay, good. So that's it. Let's box it. Okay. Good. Any questions so far? Okay. And you can realize that this is like non-dimensional, and whatever inside is non-dimensional. These are all non-dimensional. These are non-dimensional. This is non-dimensional. Okay. Good. Good. Okay. Now, you can actually solve this problem with different geometries. And so I recommend you to check page, what is that? 282. Check page 282 in your textbook. To see how you can get the center temperatures for different shapes. It's basically figure 18.3. And also, I recommend you to have a look at example 2 on the same page. See also example 2 on page 282 to 283. Okay. So this is where what we have discussed so far relates to the textbook pages. And yeah, you can calculate the center temperature, for example, for this case as well. For this particular problem, slab geometry, you can estimate the center temperature as theta center is equal to sum from k is equal to 1 to infinity 4 over pi to k minus 1. So the center means where psi is equal to 1/2, right? Sine 2k minus 1 pi over 2 exponential minus 2k minus 1 squared pi squared t tilde. And you know that the pi over 2, the sine of pi over 2 gives you 1, right? You get basically plus or minus 1 because the pi over 2, you get also 3 pi over 2, you get also 5 pi over 2, and so on. So this is basically -1 to this is all odd now, I guess odd numbers. So yeah, for 3 you get, okay, maybe you can just leave it here. But you can actually write it like as a power of -1. Let's see, pi over 2, 3 pi over 2 gives you the -1. Okay. Well, actually, it depends on the sign of the k. Yeah, that's good. So that gets k plus 1. There you go. So you can write it as theta center is equal to sum from k is equal to 1 to infinity, 4 over pi 2k minus 1 to k plus 1 exponential is 2k minus 1 squared pi squared t tilde. There you go. Okay. Or you can also use the figure 18.3 to find out central temperature for different geometries, even for the slab. Okay. So this is a series solution, series expansion solution of the temperature. Generally, if you increase the value of the k, you get a smaller and smaller value. So you can actually make an approximation and take like just a couple of first few k values to approximate the theta. Okay. Unfortunately, we don't have an analytical solution other than this type of serial solution. So this is also called an analytical solution. This one is an analytical solution, but it's a series sum, so you need to basically approximate the answer using computers or calculators. Very quickly, let me briefly mention about a couple of things. Just to wrap up. Okay. One question we can ask is, how do we solve this problem if two sides of the slab have different t? So we're going to use what we learned so far, and we're not going to reinvent the wheel. We're going to use superposition. Okay. Remember the trick that we used in two-dimensional steady-state heat transfer? We're going to use the same trick. We're going to decompose the problem into two problems. And imagine this is TL prime, and this is TL. Okay. And let's superimpose the following two problems. In other words, decouple into two problems. Okay. In one of which you have T0 and or maybe TL, let's call it. Yeah, TL and TL on two sides, but unsteady state, plus the same geometry, but this side is TL prime minus TL, and this side is 0, and this we're going to treat steady state problem, okay? And for the left-hand side, the system on the left, you have this equation, del squared theta unsteady state over del psi squared is equal to del theta unsteady state divided by del t tilde. The one on the right-hand side, since it's steady state, the time derivative is going to vanish. So you're going to have the del square theta s over del psi squared, s for steady state, is equal to 0. Okay. And if you add the two equations, if you add the two equations, you would get the following. Del squared theta u plus theta s on the left-hand side, del psi squared, is equal to del theta u plus theta s divided by del t tilde, using the fact that theta s is not equal to, is not a function of tilde, right? Which tells us that del t theta steady state over del t is 0. It doesn't change with time, so you can actually add this without any problem, right? And the boundary conditions add up nicely. I know we ran out of time, but just in 2 minutes, let me finish this. The unsteady state one gives us at x is equal to 0, t is equal to t0, right? And for steady state, at x is equal to 0, t is equal to t L. So this is TL, I'm sorry, TL prime minus TL. At x is equal to L, t is equal to TL. At x is equal to L, t is equal to 0. And if you add the two, gives at x is equal to 0, you get t is equal to TL prime. You recover the original boundary conditions, equal to TL. There you go. So basically, if you solve it for the two problems separately, then you add the two functions and you get the solution for the original problem, which is this one with different boundary temperatures. Okay, so we're done. Any questions so far?
Can you scroll down just to the final bit, just for a second?
Sure. We add the two boundary conditions just to see whether they give us the correct original boundary conditions. Okay. So this is just to illustrate that if you solve the equation, or if you find the solution for the two separate systems, decomposed systems, then the sum of the solutions give you the solution of the original problem. So that's a trick that we had used earlier for the two-dimensional steady state problem as well. But this time we decomposed into one unsteady state, one steady state problem. Okay.